Hey everyone, and welcome to the Year 11 Mathematics Specialist course. This is the second step up, the next step up from Maths Methods. So you've got 3 math courses, you've got Apps, Methods, and Specialist, and they're considered to be mounting in difficulty. Personally, I found Specialist easier than Methods, and I think the reason that is because Methods and Specialist, while they're taken together, I think focus on 2 very different things. Where Methods kind of focuses on building like your raw computation skills and ability to crunch numbers, Specialist focuses more on abstract sort of concepts. So once you're able to get those to click, I think Specialist gets a lot easier. And I'm hoping that you guys experience that click as well over the course of these videos. And if you don't, making sure that you're asking questions to both me in the comment sections and your teachers. So in terms of what to expect in this course, this is what I've basically just pasted from the SCARSA syllabus. What Specialist essentially does is it allows you to build on some of your understanding in Methods. So Methods kind of builds the baseline of mathematical concepts, and Spec kind of applies that in a more broad range of contexts, in a slightly more abstract sense as well. It also approaches mathematics in a much more formal sense in terms of in the branch of proofs and arguments, being able to show that some numerical property exists, and being able to present a structured argument or a structured proof that demonstrates that. It also introduces you to more abstract concepts like complex numbers, and also representing real-world situations in mathematics. So for example, in the form of vectors and matrices as well. There are a couple of units within the Specialist course that I would kind of consider like standalone branches of maths, but I think a big part of succeeding in Year 11 Specialist and Year 12 Specialist is being able to see connections between a wide range of disciplines within the course. So don't consider this, even though I split this course up as individual sections, I want you to think about it as all kind of playing into each other. And you can have questions that kind of ask you about complex numbers and actually have some things associated with vectors, sorry. So there's a lot of overlap, is what I'm trying to say, between a lot of the units that you're taught in this course. So in terms of recommended textbooks, these are the textbooks that I used, and I thought they prepared me pretty well for Year 11 Specialist and also Year 12 Specialist using similar textbooks. So you've got the Sadler Mathematics Specialist textbooks. These are the textbooks that generally have good explanations of the concepts. They get you a baseline understanding of what's going on. I'm going to try hash out a little bit more and explain a little bit more on those Sadler textbooks. I think a lot of what my content is based on the Sadler and the way that it's presented in Sadler. Nelson also provides okay explanations and I think slightly more difficult problems, and the OT Lee revision series basically is just a question set. So this is like it's basically just a question bank. I find that OT Lee questions are generally more difficult than exams and tests. So if you're finding OT Lee questions easy, that's generally a good sign for your tests and exams. OT Lee does also sell a textbook. I don't have a lot of experience with it, but I know some of my students that I tutor do use the OT Lee textbook and they find it quite helpful. And I think those questions are also about on par with the Nelson questions, or even close to like the revision series style of question. So let's move into the syllabus. So the Introduction to Year 11 Mathematics Specialist ATAR. I haven't exactly followed the order that it's taught in my school, and I don't know if I'll be following the order that's taught in your school, but I've had a look through the syllabus and this is the order that makes the most sense to me. I've split a couple of the sections that are listed in the syllabus up into different parts, so I talk about them at different sections along this video series. But hopefully if you follow it through, or if you decide to watch individual videos, it'll make sense to you. So the first topic that I'm going to be covering is SCARSA Unit 1 Topic 1, not Unit 1, yes, Unit 1 Topic 1, and also I've chucked a little bit of SCARSA Unit 2 Topic 3 because you kind of revisit proofs at the end of the course as well as like a bit of a revision, because the Year 11 Specialist course, I would say, is very, very proof heavy. So this is geometry and simple proofs, and kicking it off, we will be starting with simple proofs. So we're going to be looking at mathematical statements, implication, converse equivalence, negation, inverse contrapositive, and more specifically, we'll be focusing on those implication statements and being able to prove those implication statements using a wide variety of techniques, including proof by direct proof. We have proof by contrapositive. We have proof by contradiction as well. We'll also be introducing a couple of notational things like quantifiers for all, which is kind of represented by an upside down A, and there exists like a sideways E. And also being able to prove or disprove results using examples as evidence or counterexamples to disprove things. And that 2.3.1, proving simple results involving numbers, I've just chucked that in there because that's kind of something we look at just by definition by looking at proofs, because often you're proving results using numbers. And that'll also be something we revisit in Unit 2, Topic 3. The next thing we move on to is circle properties and proofs. So a lot of this proofs stuff is kind of focused on geometry. It's also focused on numbers, as we'll see in the second semester of Specialist, and we also kind of look at some trig proofs as well. Generally, you look at a lot of proofs, but for now, we're going to be looking at circle properties and proofs. A lot of this, I'll be basically listing a bunch of different properties of circles, and in Specialist, you'll be given, like, for example, a geometric representation of something, and you'll be asked to prove a certain result. And what that requires you to do is to see where you can kind of apply some of the theorems, circle theorems and circle properties that you've learned in this to prove certain results. Okay? And so this is part one, where I'm going to be introducing each of those different theorems. So this will be quite a dense topic, where I'm just basically introducing you to all these theorems that you want to later be able to apply in actual proofs. And so this is part one I've labeled, and part two, I'm basically just going to be going through worked answers of geometric proofs, situations where you're given circles or other geometric representations and asked to prove certain results. Then I'm going to move into vectors. The circle geometry and the geometry introduction to proof section also has a subsection on vector proofs, but I figured it didn't make sense to just have that there without introducing vectors formally yet. So that's why I've taken a hiatus from geometry and the introduction to proof into vectors. So the first thing that we do with vectors is we look at vector notation. This vector notation is different to the vectors that you get introduced to in physics. In physics, you kind of talk about magnitudes and angles. In the case of Specialist, you kind of look at vectors in terms of component form in a Cartesian plane. And it's important that you're able to distinguish between those, because in the WACE curriculum, physics won't accept component form vectors, and spec usually can also accept physics written vectors, but generally they prefer component form. So just make sure you're separating those two subjects if you're doing them at the same time. In terms of vector algebra, that's the second thing we're going to be moving in. We look at the scalar product, we look at some projections as well, we look at adding vectors, subtracting vectors in terms of like their components, and yeah, I think that's the main thing here. Then we have a look at real-world applications of vectors. We look at parallel and perpendicular vectors. We also look at relative vectors, which isn't formally introduced here. We have a look at displacement, force, velocity problems, which are often the most difficult problems. And if you're trying to solve them on class pads, they can give you a lot of difficulties because the class pads notoriously take a really, really long time to solve these. So I'll show you some other techniques that you can use that don't involve this really long class pad process. And we'll go over that when we do that. So now we're finally circled back to vector proofs, which basically plays into some of the stuff that we were looking for in geometry. So sometimes this actually isn't taught, and you have geometry kind of taught after vectors, and then you have them all together. Regardless, in your semester 1 exams, you'll be dealing with circle proofs and also vector proofs, and so I'm introducing vector proofs here after I've formally introduced vectors. So the next topic, this is the SCARSA Unit 1 Topic 1, but this is the topic that I'm introducing third. I think the reason it's normally taught first is because it's kind of a standalone topic. So that's something I mentioned at the start. This topic kind of isn't really related to a lot of the other stuff that you are taught in the Year 11 spec course. It builds on a bit of the stuff that you deal with in Year 11 methods in terms of your combinatoric stuff, but it looks at it in a slightly more abstract sense and a slightly more abstract sense. So in methods, you're introduced to combinations. In spec, you're additionally introduced to permutations, which I argue actually helps you understand combinations a bit better. So one of the ways that I was, something that's always stuck with me was that what my spec teacher said and what a lot of textbooks say is that a combination lock should really be called a permutation lock. So permutations involve that the order matters. Like if you're rotating your lock, you need to have each number sequentially, right? Let's say your locker number is, you need to turn it to 30, then you need to turn it to 20, and then you need to turn it to 13. You can't turn it to 20, then 30, then 13. Okay, and so in permutations, the order matters. Okay, so it should really be called a permutation lock rather than a combination lock, because in the case of combinations, it doesn't actually matter what order you turn it in. Okay, I hope that kind of makes a bit of sense. So after we look at permutations, we kind of look at some principles, and the combinatorics topic is very principles focused. Okay, so you'll be introduced to a couple of principles over the course of this. The inclusion-exclusion principle, it's relatively self-explanatory. We'll have a look at what that looks like, and I won't go over that too much now. The pigeonhole principle as well is another principle. It's relatively, when you get taught it, it seems like completely straightforward, completely logical, but when you're trying to prove results with pigeonhole principle, it can get quite difficult. Combinations, this is basically what you've been taught in Year 11 methods, but it extends your understanding of that, and you actually more deeply dive into Pascal's triangle and results involving Pascal's triangle, which can get a bit tricky. And I think there's usually an investigation that focuses on Pascal's triangle in the Year 11 spec course. Okay, so the next thing we have is trigonometry, and this is moving into semester 2. In this section, I think I've mainly stuck with how the SCARSA syllabus teaches it because I think it makes sense. Okay, so the first thing we have a look at is trigonometric functions and their reciprocals. We have a look at graphing normal trigonometric functions, normal trig functions. We have a look at graphing reciprocal trig functions, and we can see that there's a bit of an interplay. We talk about the relations between the normal trigonometric functions and their reciprocals, and some of those properties allow us to graph them a bit more easily. Okay. Then after trigonometric functions and their reciprocals, we have a look at trigonometric identities. We have a look at the angle sum difference and double angle identities, Pythagorean identities, which are very, very useful. We look at sum and difference rules, product rules. We look at the auxiliary angle theorem, triple angles as well. And this is sort of the proof side of trigonometry. So I found these a lot of fun, and I hope you find them fun as well when I teach them. Next thing we do is we have a look at real-world applications of trigonometry. For those more practically minded, this will probably, hopefully, tie in a lot of the stuff that you learn in the trigonometry course. So yeah, cool. So that's trigonometry. We move into matrices now, which is the second topic of SCARSA Unit 2. Matrices, I think, are really, really powerful. They're very useful in a lot of branches of mathematics and a lot of branches of engineering. In the case of university level mathematics, there is something called linear algebra, and matrices play into linear algebra a lot. And you can see in linear algebra that they are very, very powerful. So the first thing I want to do with matrices, basically what they are a large collection of numbers organized into a kind of table, okay? And what we can do with those large groups of numbers is we can do some operations with them as like a collective. And when we're looking at matrix operations, we can consider matrix, how to write a matrix is what we're going to do here. We're going to look at matrix addition and subtraction, which you deal with in mathematics applications, not methods, but you also introduce matrix multiplication, multiplicative identities, and inverse matrices, which is kind of like our, no, not really division, but you have matrix multiplication, identities, and inverses. We have a look at determinants as well, which allow us to compute the inverse of a matrix, and we'll understand all of these concepts a bit better when I introduce this formally. We also have a look at geometric transformations. So we can see matrices actually, other than computing these raw numbers, actually allow us to introduce transformations to certain points on a Cartesian plane. So if we have a coordinate on a Cartesian plane, we can multiply that coordinate by a certain matrix, or we can add a matrix to it. And by adding that matrix, we can change the position of that point on the Cartesian plane. I've labeled these geometric transformations. It actually also includes translations, which means like moving a point like 3 units to the right or 2 units up or down. Those aren't considered geometric transformations, but regardless, I've included that here as well. Then we have a look at systems of linear equations. Okay, so systems of linear equations, you've probably been introduced to the concept of simultaneous equations, having to solve 2 equations at the same time and see where they intersect. In this case, we kind of expand that a little bit. We can talk about systems of linear equations. It's only 2 variables here. Yeah, okay, so here we're looking at 2 variables. This is another approach to how you've already been taught to deal with simultaneous equations. And in year 12 specialist, you kind of expand this into 3 dimensions, and you can solve properties in the XYZ plane and simultaneous equations, 3 simultaneous equations, XYZ, in the 3D plane. For the purposes of year 11 spec, you don't need to deal with that yet, but I find this one quite fun, and you can think about also what would this system of linear equations look like in a 2-dimensional plane, in the Cartesian plane. What is the how would you see that on a Cartesian plane? Okay, so the next thing we move into is real and complex numbers. This revisits some of the stuff that we've done in the introduction to proof. So we have we kind of look at we revisit some of the proofs that we've looked at, direct proofs, proofs by contradiction, more specifically involving numbers. So we prove simple results involving numbers, proof by contradiction for rational and irrational numbers. Proof by contradiction is most commonly used for irrationality proofs, like proving that the square root of 2 is irrational. Then a big part of this topic here is the proof by mathematical induction. And the proof by mathematical induction has a wide array of applications, and I've also dealt with that in university level math too. So you can, this is a really powerful mathematical tool that has a wide range of applications. And so having a good understanding of that is really important if you're pursuing university level maths. And I'll hopefully be able to explain it decently well over the course of this video series. Then we move into complex numbers. Complex numbers, hopefully, as you'll find, aren't that difficult to understand. It basically, the only reason is that you have this extra component that is attached to the number known as I, and I is the square root of -1. So previously we said that the square roots of negative numbers don't exist. In the context of complex numbers, they do exist, and they are multiples of the square root of -1. So 2i would be 2 times the square root of -1. Okay? Cool. And we have a look at complex conjugates, etc., etc. We'll also find that complex numbers can be represented on a plane. So you can consider a plane as comprising an imaginary component and a real component. And if you consider your complex number, you can consider it as having some amount of real in it and some amount of imaginary in it. And as a result, you can kind of represent it as a point on that plane. And we'll go over that a little bit in a bit more detail over the course of this video series. Finally, we have a look at complex polynomials. Okay, so in the case of, if you looked at the quadratic formula previously, in some situations you see that you have plus or minus the square root of a negative number. That is, your discriminant ends up being negative. And usually in the context of the real numbers, you basically say there's no solution to this parabola. And the parabola kind of looks like it doesn't intersect with the x-plane at all. In the context of complex numbers, it does actually intersect with a plane. And we'll be having a look at how we kind of figure that out in this topic. And this topic is the last topic of the Year 11 Mathematics Specialist course. The reason why complex numbers are taught at the end of the course is because they directly play into Year 12 Specialist, because the first topic of Year 12 Specialist is in complex numbers. But yeah, so that is the entirety of the Year 11 Specialist course, and I'm excited to get into that one with you guys. Make sure that you're asking questions along the way, and I'll upload supplementary content at the end of the video series for any questions that are posed. So make sure that if you do want to try and self-learn this, that you are asking questions frequently so I can answer those. Okay, cool. That is the introduction to spec. Thank you for watching this one, and I'll see you in the video series very soon. Bye, guys.